Hello everyone, welcome to the first in a series of videos about Chapter 16. Today we'll be covering the first section where we will introduce mechanical waves. So to talk about waves really is to talk about ripples, to talk about pulses, things that we actually see in the real world. So this isn't so much as a spring block system off in a textbook graph, but you do notice this kind of behavior of waves when you're near water. So best example of that is you're skipping rocks, or in this video we see the ripple. So you'll note then that there seems to be a few sort of circles, one after the other, this pulse of water spreading from the center, propagating outwards. This is, after all, a wave. And just a few more examples. If you ever gone to the gym, there's this battle rope exercise, and speaks for itself, but you see how the person doing the exercise essentially shakes the ropes up and down, and in doing so, there's this big sort of hump that moves through the rope. This is also a wave. And if we go to a baseball game or a football game, sometimes everybody in the audience does what's people call the wave, where everyone in the audience takes turns standing up and down, and then the audience next to them does the same. So this, like I said, is also an example of a wave. And between all these examples I just showed you, the principle's the same. We had this pulse being carried through a medium, whether that was in the water or rope or a crowd of people. And this pulse, right? Nothing moves with it but the pulse, right? So the handles of the rope remain on the woman's hands. The people standing up and down in the football game are not moving with the wave. They pass the wave, but they kind of remain where they are, just sitting up and then sitting back down. And the idea then is that the way that the wave disturbs the medium where it's passing through um, affects different parts at different times, right? So while some people are standing up, some people are still sitting down in their seats. So there's actually two kinds of waves. The ones that we see in ripples or in the last videos I showed you, those are mechanical waves, and that's simply when there's this vibrations, there's this pulse that moves through a medium. So this is essentially the medium itself oscillating or vibrating as a energy moves through it. And the other type of wave is the electromagnetic wave. Electromagnetic waves are actually carried by photons, and they are really interesting because they can propagate in a vacuum. So they're not, a pulse that disturbs particles of a medium, but rather they are a wave-like and particle-like photon that oscillates through space. And we'll talk about them a bit later, since some of their properties are unique to them. But overall, we can actually describe all kinds of waves with some similar mathematical constructs. So in general, what a wave does is it's transferring energy through a medium, or even, passing energy from one medium to another. So you can have multiple lengths of a rope of different thicknesses strung together and send like a shockwave through them. And like I said, they don't actually transfer matter. So if you're you recall, if you're kind of swimming in a pool or in the lake and there's like a few tiny waves of water that pass by you, you'll feel like you rise up and then back down. The wave moves past you, but you don't move with it. So for a mechanical wave to exist, then there needs to be some initial disturbance. Since it's a transfer of energies, there must be something that gives it that initial pulse, that initial push to create that disturbance that moves through the medium. And also, the medium needs to be something that can actually be disturbed. So it's hard to perhaps send a wave through very stiff material because the elements, the particles of the material, like hard metal, are hard to give it a shake. While something like a rope is easy to shake up. And of course, the idea is that for the wave to pass through a medium, then the medium needs to be connected somehow. So obviously, a rope is, every part of it strung together. So one vibration passes on to the other. Water is all in the same pool. And if you have like a wall, between two pools of water, of course, a wave won't pass through the wall, really. Here's a nice figure from Flipping Physics. Speaks for itself, but you'll note that the pulse is effectively moving to the right without doing anything but moving each part of the hose up for a bit and then back down. And there's actually two types of waves where you have the movement of the elements as the wave passes through them move perpendicular to the propagation of the wave. So this is again like being in the lake and having waves of water kind of float you up and back down as they move past you. That's a transverse wave. That's again when you're tugging the rope, the pulse moves bits of the rope up and then back down, but the rope moves to the right, like in the graph here. A longitudinal wave, though, is when the sort of disturbance or direction of oscillations of the elements as the wave passes through them are actually aligned with the movement of the wave. So you can think of that as kind of like pulling a slinky away from the wall and then kind of like shaking it towards the wall. You'll see that bits of the slinky begin to oscillate from your hand towards the wall, and this is a longitudinal wave where you're sending a pulse to the wall, and along that direction, the slinky is contracting and expanding. So there's different bits where the slinky is more farther apart, and then as the pulse passes through, the slinky contracts. So there's kind of like this pulse here that moves to the right, and as it does so, it contracts everything near it. But as the pulse keeps moving through, the parts that get behind kind of go back to normal again. The most sort of prevalent example of longitudinal waves, which we'll focus on in chapter 17, are sound waves, where we receive those since they consist of air vibrations reaching our ears. So, a nice comparison of the two types of waves here. So, right, note the longitudinal wave, how the slinky kind of spreads in and out, while the transverse wave, the hose moves up and down as the pulses move to the right. So like I said, waves transfer energy, not matter. So you'll note then that in this particular pulse sent through this hose, the point I highlight here, right, it gets displaced a little bit while the pulse passes through it, but eventually returns back to its original position. You'll also note that if you follow the blue hand there, it gets displaced a little bit to the left and quite quite a bit up. So this actual wave is actually not transverse or longitudinal wave, but it's actually a combination of both, since it's shaking up the medium both horizontally and vertically as it propagates to the right. And that's a realistic wave, because in the real world you won't find something that's purely longitudinal or purely transverse due to all the physical effects that are happening. In fact, another example of a wave that's actually a mixture of longitudinal and transverse are waves in the deep parts of the ocean, where as the water moves over the surface, each sort of element of water kind of moves in a circular path. So things in the water are moving up and down, left and right from their equilibrium position as the waves pass through them. So, quick quiz. In a long line of people waiting to buy tickets, the first person leaves, and then people step forwards to fill the gap. As each person steps forwards, the gap moves through the line. And what kind of propagation is this? Well, if you think about it, we saw in the football game that was a transverse wave, since people are rising up and down from their seats, even though the wave's being passed um, to their sides. In this case, people are stepping forwards, and people are also moving forwards to fill the gap. So the way that people move about is in the same direction that this motion of people moving to get the tickets happen. So this would be a longitudinal wave. So this one asks about the wave at a baseball game. Like we said, people are standing up and then back down, just raising their arms. But then the pulse itself moves around the stadium. So the movement of each person, which make up the medium in this case, is perpendicular to the pulse, the big wave. So this would be transverse. So like I said, waves can take any form. Again, at their simplest, it could be a longitudinal or transverse pulse. And unless, in an ideal case, unless there's some disturbance happening, we have the assumption that a wave travels through the medium undisturbed with a constant wave speed, which, if you recall, with the spring block system, the frequency of oscillations of the spring depended on the spring and the block. It's the same idea with the wave speed, where it really depends on the medium the wave's pulsing through. So, considering just a transverse wave for now, is you're sending a pulse and the medium only moves up and down. And as you can see in the graph on the right, since the medium is moving with some wave speed v, then as time passes, the pulse will be farther and further along to the right. You can actually then calculate how much the pulse has moved. It's a simple matter of its speed times the time that has passed. So the best example here, following kind of the graphs, is that we'll have a bit of a rope sort of hanging on the x-axis, and we'll just send the pulse to the right. And the question is then, how do we talk about this functionally? We saw in the spring block system that you could use a sign function to talk about the position of the block at any point in time. But now we can talk about the position of this whole string. But to do so, then we need to keep in mind that different parts of the string are disturbed by the pulse at different points in time. So if you look at the graph A here, right, this part of the string near the y-axis being disturbed, while the part further to the right is not, but at a later point in time, then the area on the origin is much less disturbed, especially on the left side, while this area is now being quite disturbed. So in other words, we need to specify where in the element we're looking at, which particular point of interest is it over here, and also at what point in time, because the pulse is traveling through them. So we are going to try to set up this description. We want to talk about the y position of any part of the string. So y is going to refer to the transverse position of the string. In this example, since the pulse is moving exactly on the x-axis, then the transverse position is exactly the y position of on any point on the string. We're not being specific yet. So like I said, we need to account for, okay, the horizontal position of each part of the string. We need to specify that as well as the time. So we know that each point will sort of displaced upwards by the pulse and then move back down to its equilibrium position along the x-axis. And effectively then, what we call our wave function, this description of the displacement of any part of the medium, any part of the string about its equilibrium position, we're going to call that the wave function. And so again, we need to specify position and time. So this is a function of two independent variables. Now, however, if you don't care about the time variable, if you fix time to be either at 0 or after 10 seconds have passed, then what you get is a function of the horizontal position. Essentially, you get a snapshot of the whole string at a point in time. If you want to specify the position, so at x equals p, then what you'll get is a single point on the rope as a function of time. So you'll see how that point gets shaken up and down as time moves and the pulse moves. So what I mean by fixing time is, for example, in this video, they send the pulse through and there it is. It's a little fast, but if we slow it down, we can see it better. So the idea is that, right, like what we're seeing is the pulse move to the right over the course of just 1 second. But if we pause the video, we now see, right, the entire string at a particular fixed point in time. So this is what we mean when we talk about the wave function by fixing time to a particular value and just letting it vary as a function of x. We get to see the whole wave at a single point in time. And then at a later point in time, we see that as time passes, the pulse moves to the right. So the wave function needs to account for that movement. So like I said, if you lock down time to a particular value, then you can just go ahead and graph your wave function. And in this case, then you get a picture of what the wave looks like at a particular point in time as the pulses pass through them. You can also, again, fix the position and let time move forwards. So in this graph, then we set x equals to 0, which means let's just look at the bit of the rope that's right at the origin. What is it doing as time passes? And so this graph is showing you how as the pulses pass through this particular position highlighted in yellow, the point moves up and back down over time. So a quick example here in the textbook, which gives you a formula for the wave function, and we want to see what the wave functions look like at different snapshot of time. So you're describing the whole function as a function of x at different points in time. And basically, if you'll note that we have a term for the horizontal position here and term for time. So this term here accounts for the speed of the wave, because as t gets bigger, as t passes, then this overall term will shift the wave farther to the right. If you'll recall from what we learned about graphs back in the days of pre-calculus, was that when you have x minus some term, that constitutes a horizontal shift in a function. And if it's a negative sign, like here, -3, that's actually a shift to the right, telling us that the wave actually moves right over time. If there was a positive sign, that tells you it's moving to the left. So this is a function, and again, we're just going to snapshot a particular point in time, and at time equal to 0, if you graph the function, you see the pulse is passing right through the y-axis. And if you graph it at a later time, after 1 second has passed, the pulse moves further to the right, and then the pulse keeps moving. Then we ask, well, what if we had a similar wave function with a 4 on top rather than a 2? What would that change? So you'll note that everything else of the wave function is the same. So the speed here is still 3 centimeters per second, and it's still moving to the right. So what this changes, right, is this effectively is our amplitude, right? This term 4 is being a constant, a coefficient, determines the max height, the max vertical displacement that any point on our string can achieve. So compared to the original function that we had, we went from 2 to 4, which means that our maximum height, the maximum height of the pulse, the pulse itself then has gotten twice as tall, which means that all particles will reach an amplitude twice as high as before. That's all for now, and I hope you join me again when we talk about section 16.2. I'll see you next time.